know how many people have already gone through the recordings of the 2 lectures. Who has gone through the recording of and gone through the notes on design of wastewater systems? Melvin Anthony is probably the only one who has gone through them. And McHugh, it is very examinable. Everything that you went through will come in the exam. So we better what am I saying? We better really go through them. The reason why I send them is because so that we do not lose those 2 weeks. Those 2 weeks when we were supposed to. Those 2 weeks when we were supposed to, because school started on 2nd. Now we are kind of in the 3rd week, or is it 3rd or 4th? With the 4th weekend, so that we are not late. That is why. Notice already that we are supposed to be thinking about cuts already once we are done with the conventional wastewater treatment systems. And next week, in the next class, I think tomorrow we are going to look at, we will now start looking at design principles. We will be in a position to take our cut. So we will do tutorials next week. And then the week after, we can take our first cut. So again, although tomorrow I was hoping to have a physical class, or we can have a physical class for you, for your class, we can have a physical class next week. So that tomorrow we also do, but if I do for you, that means also for the rest, I do an online class. So tomorrow we can still have an online class so that we can be able to go through, start the other segments. And then next week, now we can have a physical class whereby I will talk a little bit about the course, and then we look at already the tutorials. Remember, I will still give a set of tutorials. And just the way we do with my courses. Before we start with the course for today, I think I already posted a note on water supply systems. And so, sorry, conventional water systems. Sorry. There's another, and I think I gave another, I already posted it. Introduction part. So today I want us to start with the introduction. The general introduction, and then we'll go to wastewater systems. Any question? And now if you have not joined with the microphone, I'm gonna send you out of the class. And I wonder whether you will not be able to rejoin because I will be sending you permanently for today. Again, for the entire class, attendance for me is usually not optional. Attendance is usually not optional. All right. Any question? Charlene, Jerry, Sean Minor. Any, I wonder, so that I can also know that we are communicating. Brian Cheruiyot, Brian Obumba, Brian Kipkoech, Caleb. Any questions so far? Any questions so far? Again, we are 19. I think your class is about uko 70s tukienda uko 80s. 17, about 20, it's not even a quarter of the class. Nonetheless, personally, maybe I've cared too much. You can attend or not attend. So let us look at introduction. And when it comes to this design course, design of water and wastewater systems, we are looking at a water supply system. Essentially, you're looking at the water from the source to the treatment to the distribution system. And then that is now the water part, water supply part. And then the wastewater systems. Once now the water leaves the distribution system, it is delivered to users, and from the users it now becomes the product is wastewater, and now it gets into a wastewater system, starting with a conveyance system, a collection system, conveyance system, and then finally a wastewater treatment system. So essentially you can look at what we are doing as a continuum from the source of water. For example, if the water is rainwater, water that is coming from a catchment area into a reservoir, then from the reservoir into a treatment plant, from the treatment plant into a distribution system, storages into distribution systems, to users, and then into sewer systems, and then into distributions, into wastewater treatment systems. And in each and every step, whether it is in the catchment, you have to design that particular system. For example, if you're trying to look at a source of water, let's say surface water, river water, you want to look at what is the yield of the catchment. Normally, you look at what is the yield of that catchment, and is that yield going to be able to sustain your demand? Then again, you also want to look at what are the water quality characteristics of that water, and is it suitable, is it adequate, that water characteristic, is it enough so that you can be able to use it for the desired use? Remember, you have, when it comes to use, you have various uses. But of course, here we are going to focus mainly on for supply, for domestic water use. But again, you can look at that yield for irrigation. And when you're looking at the water quality for irrigation, when you're looking at the water quality for industrial use, then, the water quality requirements vary. So basically, when you're looking then at a design, so that is now when you're thinking about the catchment area and the yield, and you have to think about it, and when designing, you have to design it. When it comes to the storage, and probably you will look at this in water resources engineering, that is where we have dams and reservoirs, and you have to design that capacity of the dam. You need to store enough water so that it is in a storage that will be able to supply your demand throughout, whether it is during a drought period, whether it is during the rainy season. You really need to design the capacity. And then from the dam, you take the water into a treatment plant, and you have now also to design the capacity so that you can be able to remove undesirable parameters and bring back the water quality to desirable, to water quality levels or concentrations, water quality parameter concentrations that are meet set standards. In Kenya, we have a number of standards. We can use a number of standards, and this is probably something you have looked at in public health. And so that we can, so that we can interact. Anyone who can tell me one of the water quality standards that we can use in the country? And that is one. Then two, if you are thinking about water quality standards, which body do we look at? Brian Cheruyot. Wacha nianze because now my names are ordered in alphabetical order. Cheruyot. Any standard you know? One, Brian Kipkoech another, Brian Obumba another. Caleb Mukenya. Anyone who can tell me about Brian Obumba, some of an example of water quality standards we can use in the country? Brian, you were speaking. What has happened? Your microphone is still on. Anyone who wants to volunteer? Chebi, Zephania? Someone, save us. Microphone. Sorry, Brian. Next time you can work on your microphone so that we can be able. But maybe you can type and say which one. pH. Yes, pH is one of the parameters, but the question is, in Kenya, if you want to know the set standards, like what does our country definitely, no, jurisdictions, regions have set certain standards. For example, they have said for drinking water, the water the pH should be between maybe 5 and 8, for example. And there is a document, or when it comes to chlorine, when it comes to fluoride, which we know has detrimental effects, when it comes to nitrogen, there is a document where you can you get information about the standards that are allowable in the country for various parameters. Which body? Water Resource Authority, WRA. So I was asking, that is Chebi, which department provides such kind of documentation, and which documentations are these? Now, pH, Brian, is one of the parameters. Water Resource Authority is a little bit much higher. There is Kenya Bureau of Standards is the body in the country that regulates all the standards in the country. And some of the water standards we use in the country, we have national standards. For example, you may find a certain standards in KEBS that is about drinking water quality or water quality generally, or I don't know where, and then you'll find that we have drinking water quality, irrigation water quality, surface water quality, and all those. Then, if that is a national standard, recently we are moving from national standards to East African standards due to the East African community. Everything now is being regionalized. So we have the Kenya standards, but nowadays we are calling them East African standards. Then, in addition to those, you can, for example, sometimes in the practice out there, if you cannot find a standard, you can always go to World Health Organization standards. Now that is global. That is kind of a global standard. But you find that many countries, many jurisdictions take those international standards and then they customize them or they update them, they try to modify them a little bit here and there, and for their own use. And you will find that standards in Kenya may be different from those standards in Tanzania. They may be different from those standards in the United States, and so forth and so on. So that when you are practicing out there and you see something different, you must be back in your head, you have to think about where, for which area am I doing my design, and then you apply the appropriate standards. So when you are designing, whether even it is in structures, whether it is in roads, whether it is in water, you have to think about the design criteria. And a design criteria is basically boundary conditions that establish the functional performance of the facility. For example, let's say you're doing a sewer system. One of the design criteria, which is very critical, is velocity of flow, so that you do not have sedimentation, so that you do not have abrasion of the system, so that you do not have buildup of sulfide. So velocity, you have minimum requirements of the velocity of water flowing through a sewer system. Again, even in water supply systems, velocity is also a very key design criteria. So that is one. Two, you have, like in water supply systems, another design criteria is the water hammer. So that you can be, you want to determine the water hammer so that you can be able to determine the gauge of the material through which your water is going to pass through. Those are design criteria. So we have performance criteria. We have also prescriptive criteria. So performance criteria, they define the desired objective, but not the means of achieving it. So, like I've given the example of velocity. So we want a minimum, like in water supply systems, you want a minimum velocity of 0.7 meters per second and a certain maximum so that you do not have abrasion, you do not have erosion of your, conveyance material. But you do not state how you're going to achieve the 0.7 meters per second. We have prescriptive criteria which define the explicit details of how the facility will be built. Now, when we come at this prescriptive criteria, now this one comes in the implementation part of it. And now this one, we are mainly going to focus on performance criteria. Because in most of the water supply designs, what we are making is kind of a blueprint, an architectural plan so that we can be able to give it to whether it is mechanical engineers or structural engineers, so that now they can do construct the components. We have normally a number of and now this design criteria, it is overall, whether you are dealing with the source, with storage, distribution, storage, treatment components. And in treatment components, remember, you have all those so many components. And you have already seen like the design of wastewater treatment systems in the recordings. So all those design criteria, the performance and everything, those criteria apply for each and every component that you are going to design. So normally we are looking at 6 factors in establishing the design criteria for water and wastewater systems. And then one of them is the raw water or wastewater characteristics. And these are basically categorized into 2: the quantity, the amount, and the composition of the untreated raw water or wastewater. And when it comes to, or rather, that can further be subdivided into the raw water composition, we are looking at the hourly, daily, weekly, monthly, and seasonal variations in raw water composition and availability. And each of these, whether it is hourly, daily, weekly, monthly, each of it is used for when designing certain components. For example, you may find that hourly flow, peak flow, and what have you may be required when may be used when you're designing pumping systems. Another one will be used when designing storage systems or maybe equalization tanks and what have you. For when it comes to, the first part, the water characteristics, the first part is the characteristics of water water supply systems. But when it comes to wastewater characteristics, we have the flow rate of the wastewater and its composition as well. So in water, we have demand for water and the composition of untreated raw water. But in wastewater, we have wastewater characteristics and the flow rate. And they include composition and strength of the strength of the wastewater, hourly, and so forth and so on, just like I've explained in the water. Contributions from industrial and commercial activities. We are also thinking about rainfall runoff intrusion. And then in such kind of a case, and we are thinking, we have, for example, in the sewer system, a combined or a separate system. Are we going to have seasonally separate system and seasonally, combined system? We're thinking about groundwater infiltration, raw water, mineral water composition. Now, let me not go into details of talking about these systems and, some of these contributions. And I wonder whether we are going to have an opportunity to look at some of these things later, or they are not in this particular course, because already now, during this El Nino period, although it is said that it is going to come to an end soon, probably in the next 3 days, some people are already talking about the rainfall coming to an end. Others are saying that the rainfall is going to continue up to February, that it is going to, this rainfall is going to merge with the next season. For your information, like in Nairobi, because we can relate to Nairobi, in Nairobi we have both separate systems and combined systems. The systems that were constructed before Kenya took control, those long time ago, the oldest systems are combined, I think, whereby you find sewage and stormwater flowing in the same system. And then the systems that have been constructed a little bit later, we have a separate system. And for the separate system, we have stormwater flowing in most urban areas, flowing in roadside channels, which is managed by Kenya Urban Roads Authority. And these are things that we need to know as we come out there. Then the sewer systems are managed and controlled, and maintained by Nairobi Nairobi County. I think it is the Nairobi Water, the company that deals with, forgetting its abbreviations, but the company that deals with water supply and sewer systems in Nairobi. So if you do a combined system and you're doing a system that can carry sewer and rain, stormwater during this El Nino period, just imagine what's, how big your sewer system has to be. And you have already seen that our systems in Nairobi are overwhelmed. We have a little bit of showers, and then we have flooding everywhere. And normally you will find that like in places where we have separate system, when you design a line, you may realize you need only a line of 300 millimeters. Even 1 foot is very big. You need a very small pipe to pass your water. So you design and you provide that one for, and then you implement that one is constructed. But come rainfall, and then sometimes, there's a lot of leakage of our sewer systems and what have you. Anyway, this one is neither here or there. So I really did not want to dwell on this because there is a lot to talk about in this section. Now, so essentially you need, in one of the key design criteria is the raw water or wastewater characteristics. 2, and before I leave that part, when now you're thinking about the raw water wastewater characteristics, then you're also wondering if the raw water or raw wastewater from this industry has this characteristic, should I combine that water with water from the domestic sewer system? There are so many kind of decisions that you have to make. We have environmental and regulatory standards, and with these standards, you want to know what water source can I use? What water source can I use? If this water source has heavy metals, can I use it for drinking water supply systems? Two, what, for example, I'm just giving examples here. To what levels should I treat my water so that I can discharge it into a natural water system, like in a river? After treating our water in sewerage treatment systems, of course, we discharge that water. So environmental and regulatory standards are another design criteria. Again, we have what we call system reliability. And when it comes to system reliability, we are talking about the ability of a component or system to perform its designated function without failure. So normally here we are talking about, and one of the key aspects here is provision of redundancy. What is redundancy? That, for example, if in your water treatment system, you have seen one sand filter, slow sand filter is adequate of a certain dimension, is enough to treat your water, you provide another one in parallel in case you are maintaining the one that you have, in case you're maintaining one, you have an alternative to continue treating your water. That is redundancy. So you provide redundancy for maintenance, for breakage, and what have you. And usually for critical elements. Redundancy, you can also maybe include storages that can also serve to solve the redundancy or, such kind of a problem. We have facility limits, and this is about location and area available for the treatment plant, availability of power roads, and a connection to the raw water supply or the point of discharge. For example, you cannot use facultative ponds in an area where you do not have land. In such kind of a case, you can think of activated sludge system, which are much more compact. Facultative ponds, waste stabilization ponds will require a little bit much larger area. Then again, we have the design life. Now, and when it comes to the design life, when most water systems, I don't know whether it is I don't know, is it your class or I cannot remember? You teach so many of these things and they are all interconnected. When it comes to design life, if, for example, a sewer system design life is expected to be 50 years, you want to design your structure so that 50 years later, the facility will be able to still carry, the wastewater that is passing through that system. And now that is now where design demand or design flows, design water demand or design flows, wastewater flows comes in. How do we come about with them? So normally in this kind of design life, and it is usually one of the first things you do when you're designing some of your systems, you have to do population forecasting, and so that it can coincide with your design life. And then you look at the population in future and calculate the demand. You can calculate the design flow for the population so many years later when your plant is going to be in operation. Then we have finally the cost. Of course, we cannot go, our activated sludge systems are quite expensive. And also you have to look at maintenance costs, operation costs, and what have you. Where I come from, we say when you go to a tailor, and you are doing a dress or a kabuti, you can only do according to your height. Inakatwa kulingana na urefu wako. So you can only do what you can afford. So basically, those are the 6 main design criteria that we look at, and especially the cost bit. In addition to all those that we are talking about previously, very nice talking. Kwemoy, you have to join with microphone. That is what I have, instructions I have given, and I have already posted it. Or if you can, or maybe leave. In addition, however much beautiful what we have discussed those previous design criteria are, if you cannot afford, then it is not going to be done, and we do not want not to be able to do it. So now we are going to briefly, because this one is basically an introduction, we are just looking at general, generals here and there, just general here and there. How many pages do we have? We may end up just doing the introduction today. So I want us to, and that will be our first topic of discussion, and you can submit this assignment to me privately, just half a page or 1 page kind of a thing. You can type it online, send to me and tell me, why do we need water supply? Why do we need water supply? So assignment, why do we need water supply? And that one is going to be submitted to me directly, sent to my emails, my Took email. I will post it. Send it to my Took email. Send them to my Took email. Of course, if you don't attend the class, you will not know which assignment it is. Now, so secondly, when it comes to water supply systems and design, we have already talked about water demand briefly when I was talking about design life. And like I've said, it is usually one of the most, or the very first things to do when you're starting to design your systems. And why is it needed? So that we can be able to determine our design capacity. It consists of 4 parts: selection of a design period, estimation. Okay, whatever I was talking about is here. So yeah. I was wondering whether I was going to go back and look for different. So estimation of the population, commercial and industrial growth. So you're looking at for population forecasting. So you have a design period, population forecasting, estimation of the unit water use. Unit water use is, for example, for humans, for domestic use, and we are talking about households, we are talking about how many liters per head per day are used. Estimation of the variability of the demand. For example, between 4 a.m. up to about 9 a.m., we have peak demand. Then the demand goes down. We have a minor peak over lunch hour, and then we have another big peak in the evening. That is variability of the demand. And the same variability when you look at sewer systems, it will probably follow about the same trend. So the design period is the length of time it is estimated that the facility will be able to meet the demand. That is the design capacity. Now, there are, I think I talked previously, I talked about design life, right? Yeah, I talked about design life. And notice here we are talking about a design period. There is a difference between those two terms. When you're talking about a design life, for example, if you make a concrete structure, it can survive without, much damage, maybe for 100 years. That is a design life. The structure is in existence. But let's say you make that structure 100 years, it is still standing. But can it carry the weight that you designed it for? Now, when we come to the design period, we are talking about that length of period when it is estimated that the facility will be able to meet the demand. That is the design capacity. So you may find that a structure, you may look at a structure, it is functional, it is good, it is in fair condition, but it cannot deliver the design capacity you designed it for. For example, you can design a pipe to deliver 10 liters per second, or let's say, or something like that, or 1 meter cube per second. But in future, you are required to deliver 2 meters cube per second. I don't know whether you follow, media reporting there. And I remember the governor of Nairobi was talking about why they need to ration water in Nairobi. Why? Because their capacities can only deliver so much, but the demand now is much higher. So that is usually associated with the design period, the design capacity. So we need to be able to differentiate these two. So when we are making new waterworks, we make them large enough to meet demand for future. And the number of years you select for design period is based on the following: regulatory constraints. Normally, so those regulatory constraints, you will find them in maybe a water designer's manual, a sewer bridge designer's manual, or something like that. It is also a function of the rate of population growth, the interest rate for bonds. That is, for example, if, for example, you have an infrastructure bond and that infrastructure was constructed. Now, this one is purely an economic consideration. So, for example, if the government sold an infrastructure bond, so you have to look at the interest rate of the bonds. And then you say that bond is going to be for 20 years. That bond is going to be for 100 years. Once you start working, you may develop interest in investing in these bonds. We have treasury bonds, we have, all these things. One of the robust investments you can do in Kenya currently, although due to the free fall of the shilling, people are shying away from buying these bonds. But now, this is interest rate of bonds, and especially if the source of money to construct the structure is from such kind of sources, the useful life of the structures and equipment. And when I say that, I give the example of a concrete structure. The life may be very long. So when you're designing, when you're determining your design period, maybe it is in your interest, you try to make the design period and design life as close as possible. The ease or difficulty of expansion, for example, if you're doing a stabilization pond system whereby you have primary, secondary, and tertiary ponds, those ones are massive kind of structures. How easy is it to expand such kind of a system? Then performance in early years of life under minimum hydraulic load. So again, you have to balance. You do not want to make so big a system so that in the early times, it is underutilized. It is underutilized. So that is the case. Now, typical design periods commonly employed in practice are shown in most water projects are given here. Of course, you can always find such kind of information elsewhere. So these ones are just typical design periods. We have large dams and pipelines. The life expectancy and design life are the same, but the design period remains a design period. So life expectancy is the length which we expect that structure is going to remain robust. But design period, is basically, I've already talked about it. So these are typical values. Of course, why did I leave this one for distribution systems? Distribution systems is just a repetition. It's the things to do with copying and not knowing, editing the pasting very correctly. So we say you copy what you can paste. So I think I copied just this row and I forgot to delete it after filling in the previous one. Now, so let us look at the projection years. So you are designing a project now, and you have determined that your design period is so many years. You have said you are doing a water treatment plant with a design period of about 25 years. Today is 2024 plus 25, you're going to have 2049. So you need that your system will be able to carry the capacity 25 years later in 2049. You have to do projection. You have to do projection, and normally we usually do a number of projections when we're designing our systems. We have the current population, then you have initial population or initial projection, future projection, and ultimate projection. Now, from the current is the population currently, and how do we get the current one? The last census was done in 2019. Today is 2024. So you have to do some sort of population projection so that you can be able to determine current population. You do population projection for both humans, industries, shops, all aspects of growth. So, but I hope we shall see a little bit later what I'm trying to talk about, all types of users of the system. Then the initial year is the year when you expect your facility is going to get into operation. If today is 2024 and you start constructing, you're estimating that it is going to take 2 years, 3 years to construct a facility. Then the initial year, let's say 2 years, the initial year is going to be 2026 after 2 years. The future year, I think it's supposed to be, is it 10 years after the initial year? And then the ultimate year is usually 20 years from the initial year. And once you have determined this, the current, what is critical is the initial, future, and the ultimate projections. You cannot change this. Once you have determined this, you cannot change this during the design period. So it is very critical that you get this projection right, because once you do it, you cannot change it. We are going to see later how these initial, that will be now when it comes to, when we are designing, when we go to design, when we go to population projections and determining water demand and demands or design flows, I will show you how we use these kind of projections. Then we have the design demand. I think I've talked about the design demand. Let's look at the population, commercial and industrial growth. And here I want us to look at how to do the projections. I probably am going to give you another write-up that has more formulas, more, or maybe it is somewhere, maybe it is in another. I will see if it's already in that other one. I will give you during that time when we are doing the actual design of the systems, water supply systems. But generally, when you're doing population projections, like I've said, you have to know where to get population data. And for example, I've said we did our census in 1999, and you know that census does population about everything. One, humans, cattle, camels, industries, shops, everything. It does. You are supposed to, from the census, you're supposed to get all that information. Which body does or is the custodian of population data in the country? That is number one. And two, I wonder whether we know where we can get such kind of information, census information. Anyone, any volunteer? Anyone? Sean Minor? Sean Minor, I'm just going. Violet Akoth, anyone who can state? Anyone? Kenya Bureau of Statistics is the custodian of this data. And anyone who can know how to obtain this data? Anyone who has tried to know, who can tell how we obtain this data? How we can obtain this data? It is the Kenya National Bureau of Statistics. But for purposes of progress, all this data is online. You need any reports of census from time immemorial, you are going to get this data online. Go to Kenya National Bureau of Statistics, Google, they have data, I think up to, I don't know whether it is county levels or sub-county levels. They do not just have I've not seen at village levels, but you can always get that data. In those documents as well, you will see tentative values of population growth metrics. For instance, like the growth rates of the country, you will see them in that data. Then when we are talking about the unit water use, it can be, what is the unit water use? I already gave an example. How much water per head per day is used? 2, how much water per sheep, per camel, per goat, per cow? How much water per hospital? How much water per butchery? That is the unit water use. Generally, we have some tentative, and because I will always remind us how our practices, because of our practices, we have to use metrics from elsewhere. For example, in the United States, we have some typical wastewater flow rates from recreational facilities. I wonder whether I've given water use from, for us, I will still give it. So typical water consumption rates for apartments, cabins, that is for the United States. That is from, I got this from Metcalf and Eddy in 2003. I cannot remember the name of the title, but I don't know whether I've given it in the introduction. Let me just look at the course outline and see whether I've given it. Metcalf and Eddy, wastewater engineering, treatment, disposal and reuse. So we have that one for 2000, but we have a later one. So this one is a basis of some of these things that I've given here. Which one? In introduction. So So here we have typical wastewater flow rates generated from various users, domestic, industrial, recreational facilities. Yeah, so what about water consumptions in Kenya? And you can get this information from Water Designers Manual. We have a copy from 2005. It's we have I think we have it is online, but I can always send it to you because I have a soft copy of the same. And these water consumption rates in the country are, based on a number of factors. Whatever is given, we have 20% allowance for water losses through leakage and wastage. And once you have this data as it is, you do not need to provide additional peak factors to calculate a design demand. Now, why is that? Assume you have already provided a 20% allowance for wastage. Normally in design, if you provide for one, I could call it, let me call it flexibility. When we are designing, we design flexible systems. So if you say you have water loss, you have peak flows, you have, so you need to provide for a number of, after determining the design flow or, design demand, you need to allow for this loss, you need to allow for this one, you need to allow for another. If you were to put all those together, you are going to end up with a very large water demand, and then design a very large facility. So what usually we do in design, and it is something that we also do in structures. I'm very lost with transport, so I cannot even remember many things, but I know in structures. So if, for example, you provide for fire, then you can ignore this one. You can ignore something else. So like in this case, the figures that have been provided in our Water Designers Manual, you do not need to provide for additional peak factors. You will see where these peak factors and I shall be talking that we are talking about. Why already? Because we have already given a 20% allowance for water losses. These rates normally that we have are just a simple guide, and you can adjust them based if you have more clearer information. And they are also, and probably I don't know whether I'll have an opportunity to talk about them a little in a little bit detail. They are based on a number of factors. One, you have to consider whether you are doing your water demand for rural areas or urban areas. Then you have to think about the climate of the area, especially the rainfall potential. So you have high potential that is in the Kenya highlands. So in those areas, the water is abundant, so you can use as much water. You have medium potential, and then you have low potential, that is the dry area. So my brothers from Ukambani, when you're doing your water supply and you are in low potential areas, you don't feel shy, don't feel bad when you see you can only use so much water, 10 liters per day, if you do not have a connection, for example. Then, so you look at whether it is rural or urban area. In the rural areas, then you have to consider the climate potential, the water potential. Then in urban areas, you have to think about high class, medium class, low class housing. And in these cases, you're also considering, is it an individual connection? Is it, people without connections, where we buy you have communal connections. And of course, I forgot to say, you also have to think about what kind of consumer is in question. But basically, you are looking at, is it rural, is it urban, is it high potential, is it low potential? is it the water potential, and then you're looking at is it individual connection, is it public connection. Now, you also can look at the variability in demand, variability of demand, and most of these unit demand estimates that we have seen, whether it is in Kenya, whether it is those examples that I've given for the United States, they are average estimates. But you find that, and I already explained, they change with seasons, they change within days of the week, they change within hours of the day, and normally this variation is reported as a factor of the daily average day. And in, I think it is still from the same Metcalf and Eddy, they provide a way in which we can be able to calculate, estimate factors, variability factors, or ratio of minimum or peak to average flows. And that this one is specifically for sewerage flow. So if you have estimated an average flow, then you have peak flow. You can calculate minimum flow, and that one is also related to population that is in question. Now, the demand for water supplied by municipal water systems has two driving components: consumer consumption and fire flow demand. I think we have consumer consumption and fire flow. Now, when it comes to the consumer consumption, we assess it by determining the average daily consumption, maximum daily consumption, instantaneous flow demand, and so forth and so on. And you will see later, I don't know whether it is here or it is in the wastewater systems, where I have explained when to use which kind of water demand. Then we have the fire flow demand, and you need to provide an adequate amount of water, for controlling fires. My question is, do we really have that in the country? The question is whether we really have, whether it is, actually, this is something that someone can look at. Of course, I know most of you did not take water projects, but when I'm teaching some of these courses, this is when I come and start thinking about ideas. Someone could look at, I don't know what really they can look at, but someone can look at fire flow demand. Because most of the times you find, if let's say it is burning somewhere, these fire extinguishers come and they come carrying their own water. But is that supposed to be the case? Of course, they're supposed to carry, but we are supposed to have fire hydrants. We are supposed to have fire hydrants almost all over, and we are supposed to ensure high pressure in those fire hydrants so that they can be used. They can be, functional. So this is the fire flow demand. This is an area, I don't know what someone can do, but this is something someone can look at, not only in Nairobi but in the entire country. That is a very it's an area, fire flow demand is an area where fire flow demand is a weak link, or a weak area, an area with opportunities. So I've talked about that, and I want us to look again also. It is basically introducing, this is introduction, we have not even gone to the actual thing itself. Chris Ochung, you have to join with microphone. And this is going to happen even in future classes, so that we can be able to talk to each other. And the next time I'm asking a question and no one replies, nitanyamaza tu until you reply. You'll know that I'm more stubborn. And, I'm more stubborn than you people. And by now you should have known that. Then we have water sources. I want us to finish this before we go for a break. Or we can just go for a break because it's already 8:10. Tumemaliza 1 hour. So let us, when we come, we will look at, I will talk briefly about our water sources. And we'll, let's come back after 10 minutes, that is 8:20. In the meantime, I'm going to take attendance. And remember again, for the YouTube videos, the attendance of those lectures who call will be based on the people, I'm able to see the people who have watched the videos. So let's meet at, I take a poll first before, so that I can know who is present and who is, you know the drill, and then I save my attendance for the first half. For example, Rogers Ochieng, Elvis Karumbi, Chris Ochung, hao wametupeleka Mwethia, wametupeleka tu, ni kama wale ng'ombe wanaendanga na wengine wakienda kichinjioni. So Chris Ochung, any question before we go for that break? Any question? Any question before we go for that break? So, Elvis Karumbi, you are in, okay? So let's meet at 8:20. Okay, let us continue, and this is really going to be brief. When it comes to water sources, it's important, it is necessary that we know where we can be able to get our water. And one of the places is getting water from rivers. And if it is from rivers, more often than not, you have to make impounding reservoirs so that we can be able to store enough water that we can also use during the dry season. You can also get water from freshwater lakes. Freshwater lakes, you get water from wells, and whichever system you're doing, if you're doing from freshwater, if we are doing from wells, you have also to design such kind of systems. You can get water from oceans, from bays, and so forth and so on. Now, when it comes to the water supply systems, basically, the water supply system will have a number of components. You have, I don't know whether it is here. No, I doubt whether it is in this course, and you are not going to see it. There's another material, course material that I have, which gives a complete schematic of all the components that you are going to encounter in a water and wastewater system. So starting from the source to collection works, to transmission, collection, storage, transmission works, purification works, and the distribution work. And then from the distribution work, like I had said before, you go to sewer system. From sewer system, you go to sewer treatment system before disposal. So that is the part of the introduction, and I wonder whether there's any question before we go to. I want us to go to the water treatment systems. I normally start with the design before I come to the water and wastewater systems, but it doesn't really matter. So I want us to start with water treatment systems, so that now we are ready to take our first cut. Next week we have our first tutorial session, physical, and then next week, but one, we have our cut. So in that case, I need to remember so that I can be able to send tutorial questions. So I'm going to send tentative tutorial questions. So in the meantime, if you have any question, before we proceed, and I'm not going to be talking alone, I will want us to respond to each other. I will really want us to respond to each other. So let me check where tutorial questions are. Yeah, I think I have some. So if I will update, I will mention. So we go to this, we have to look at those tutorial questions, go through them. So far, we look at design of wastewater systems, design of water systems, which we are going to do, and then the introduction part, so that we can prepare for our first cut. Any question? Any question? So let me bring conventional water treatment, conventional wastewater treatment. Those two tutorials will do for the wastewater treatment. So for the tutorials, be ready with those two parts. So let's go to conventional wastewater system. Conventional water treatment, sorry. Conventional water treatment systems. And first of all, we start by describing drinking water quality, because why do we treat water? Because we want it to meet some certain standards. I'm sure and I believe you have already come across some of these things that we are going to do, so it is going to be a repeat. But the question is, we know the science, how to treat these things. Then how do we apply that science into determining the capacities, the dimensions of these treatment units? So first, like I say, let us look at what do we want to achieve when we are treating wastewater? And we want to change the physical characteristics of that water, the chemical characteristics, microbiological characteristics, and radiological characteristics, so that they can meet desired design criteria. Desired standards or set standards. Now, in order to be able to treat our water, so that we bring our turbidity level to, say, 0 or to so many NTUs, we want to bring our fluoride to less than 0.15 milligrams per liter, for example. We want to bring our Escherichia coli to 0. We want to bring our total coliforms to 0, and so forth and so on. We want to bring our bacteria and helminths to 0, 0 number per so many milligrams. What do we do? What usually happens? We usually involve some physical, chemical, and biological processes. And most of these processes, normally these processes are usually called unit operations. Now, some of these processes can be divided into three categories. We have physical processes, we have chemical processes, we have biological processes. Some physical processes are, for example, screening, whereby you can use a screen, a sieve. We have sedimentation, whereby you can use a sedimentation tank. We have filtration, where you can use a slow sand filter, rapid sand filter. We have adsorption. Adsorption, you can use, for example, in a filter materials, you still have that kind of absorption, but you would need a material that has a surface whereby the parameters you want to remove can absorb, or rather can attach themselves to that. We have chemical processes, oxidation, aeration, coagulation, flocculation, disinfection, softening. And biological, for example, coagulation, the typical water treatment plants that we know we have the coagulation process whereby we add a coagulant. After the water leaves the filtration, we have to take it to disinfection. Now, if you're dealing with groundwater, you may need to soften it if it is hard. Also in groundwater, you may have to do some oxidation, for example, or aeration, because the oxygen concentrations are usually too low. Then we have biological processes. In slow sand filtration, especially where we have this Shimzeke layer, and I'm already talking about this because I'm imagining we have come across this processes in public health engineering, and if I can get some response about it, so that I just don't talk about things without explaining. You can have biologically activated carbon. So in the slow sand filtration, we have the Shimzeke layer that has a lot of bacteria, which, it's kind of a colony of microorganisms that prey on each other, and so forth and so on. And, because of that, they end up reducing any bacteria, viruses that may have been they may be remaining in the system. So, John Kimanzi, I wonder, have you looked at some of this, generally the typical water treatment system in say, for example, public health engineering or water resources engineering? I don't know where you're supposed to look at it, because here, of course, we will repeat, but we will be focusing on the design aspect. John Washira, who can respond? I wonder, because I also want to know the level up to which, although there's not much I can do because we have a lot of ground to cover, but it is good that I know, so that I do not talk about. Normally, when you are climbing a tree, you do not start from the branches, you start from the bottom, from the ground, so that I know how much far back I can go. Anyone? John? Ida? Anyone who can tell me? Ama nyinyi wote mko kwa matatu? Seems like I'm talking to myself. Yes, in thank you, Elvis, in PHE. So if you already have some background information about these things, that is very good. So we will just see a little bit. So those unit operations we have stated, what are their functions? For example, screening, we remove floating matter. Sedimentation, we remove suspended matter. Disinfection, we kill pathogenic bacteria, and so forth and so on. Now, when it comes to water treatment systems, I'm now realizing I gave a lot of information. But anyway, that's okay. I will still go through it. I will still go through it the way I have designed it. So we already looked at the various sources of water, and you find that in when you're in given water treatment systems, you may find that a water treatment system has a screening chamber. It has coagulation and flocculation. It has sedimentation, and then from sedimentation you go to slough and filtration, and then you go to disinfection. So it doesn't have everything. And what really drives an engineer to choose which unit operation to include in the treatment process? Of course, it is the raw characteristics of the raw water. For groundwater, for example, which is supposed to have very little suspended matter, you may find that it does not have sedimentation, but it has oxidation and aeration. It has a softening. Then after that, you find some although we expect groundwater to have little or no biological contamination, you may have some kind of disinfection in order to provide residual disinfectant before you release it into the into the distribution system. Again, you can have activated carbon as a softening kind of a thing. So because of that, we have classification of treatment systems. Of course, I've said first differences between groundwater and surface water, some differences, and this advise the choice of unit operations that you are going to include in a water treatment system. Because of that, we have what we call coagulation plants and softening plants. So in a conventional surface water treatment plant, that is their coagulation plant. Probably that is what you have seen in public health. But you can also have a direct filtration plant. And I think we should have a softening plant somewhere. I wonder. Yeah, we should have a softening plant somewhere. Softening plant, and then we also have finally membrane filtration. But I want us to focus on the softening plant, a filtration plant, and then conventional surface water treatment. This is when mostly we are learning that we come across. That is what we come across. And normally this one is used, and it is also the most common in the country and in Kenya. And it is used when we are treating surface water or river water. Of course, you select unit operations, place them in series, based on the water quality of the raw water. Now, we have a little bit of explanation of the various plants, So here we are going a little bit notch higher. You do not only deal with a coagulation plant, but you will also likely, like if you're using borehole water, you are going to have a softening plant. You are going to have a direct filtration plant, and and so forth and so on. So once you go to the ground, when you start practicing engineering, remember some of these things. Now, we are going to look at each of these unit operations one after the other. I'm not going to go to all of them, through all of them. For example, when it comes to the disinfection, it includes a lot of chemistry, but we are only going to limit it because the chemistry is, if we are to go through the chemistry, it is going to be advanced level. So we are going only to limit ourselves to what is really necessary for our level. So first of all, we look at rapid mixing, flocculation, and coagulation. And before then, I think we have, let me see, did I, screening hakuna mahali. Screening, I wonder. But I think when it comes to screens, we saw some in wastewater treatment. So the same kind of applications, the same kind of principles apply here. Only that now the debris are much, 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 much larger. For example, if you see this direct filtration, you still have a screen. The only place where we don't have a screen is, I think, softening. In softening, you'll find that we do not have a screen. So we start with rapid mixing, flocculation, and coagulation. And you'll notice all those are unit operations, but we have combined all of them into one. Why? Because it happens at the same time, especially the rapid mixing and the coagulation. No, rapid mixing occurs together with the dosage of the coagulant. So the coagulation and flocculation are usually combined in the same tank. So you add a coagulant, then I wonder, have you visited a water treatment plant? So you add a coagulant, and then immediately, almost at the point where you're adding your coagulant, you have a very rapid mixer, which really thoroughly mixes your coagulant with your water and then releases it into a flocculation and coagulation basin. Those two occur together. And then because of that, I put those three in the same, because all the activities happen together. So why do we do the rapid mixing, flocculation, and coagulation? One, it does a number of things. it removes turbidity. Turbidity is caused by the presence of suspended, very fine colloidal suspended matter, which does not settle. It moves within water through the Brownian motion. So turbidity will cause color to, causes color to be there. Of course, also chemical composition of water may cause color, but turbidity also causes color. Again, coagulation, flocculation, rapid mixing can cause organic matter, whereby bacteria is some form of organic matter in that water. So during coagulation, normally the coagulant changes is meant to induce the surface charge on the particles to change so that they can stick together to form larger particles that will be able to settle, to be heavy enough to settle by gravity. Now, how does that happen? And we have the colloidal stability and destabilization. And of course, this part I once in a while test about it. Of course, you'll find questions in tutorials related to the colloid stability and destabilization, types of colloids, types of coagulants, how they operate, the chemicals, the chemistry behind it, and what have you. And you'll notice that most of the coagulants are trivalent and ions. They are trivalent ions. Why? What is the reason for use of the trivalent ions and what have you? The common coagulant, there are some key characteristics of coagulants. When you are selecting your coagulants, the trivalent cations, non-toxic, insoluble in the neutral pH, and so forth and so on. Because if they are soluble, then remember you want to have a particle whereby you can have additional particles attaching onto it. It's like you are seeding like the way we do seeding in clouds in order to form aerosols so that water can attach. So now in this case, we are trivalent cations onto which other molecules can attach onto them. The common coagulant is called aluminium sulfate. And before I go to that, those large particles that form are usually called flocks. They are usually called flocks. And just give me a minute. So time is almost up. We have a very few minutes. So where was I? I was at coagulant. So we were talking about the trivalent, and the types of coagulants. So we have the alum-based, and then we have ion, but all of them are trivalents. Then it is very important to note how they operate. What causes the charge? Then we have coagulant 8. And these are chemicals that or substances that enhance, accelerate the coagulation process. And we have 3 types. We have silica-based, clay-based, and polymers. Basically, they are finer particles that already, and they are heavy in nature, that already now, once the coagulant has created charged ions, they are already available in order to attach to the charged ions. And already once it is attached, the colloid aid also becomes charged. So now, and then also it becomes heavy, and then it enhances the coagulation and flocculation process. We start from rapid mixing tomorrow, so that we end at that point. We end at that point today. Any question? Any question? Swali ndio tumalize. Kama hakuna, someone can just say there's no question or there's one. Any question? If there's none, so tomorrow we are starting at rapid mixing. I hope I will remember. If I don't remember, you can remind me then. So if there's none, we can have a good day, and we meet again tomorrow. Tomorrow still we'll have an online meeting. Then physical meeting next week, and a cut next week, but one. So that from today we have 2 weeks to prepare for the cut.